The harder you work for something, the greater you will feel when you achieve it. In this video, we will see three problems related to relativistic classical mechanics. The first one goes like this. Prove that the four-dimensional volume element dx, dy, dz, dt is invariant under Lorentz transformation. We are all well aware of the Lorentz transformation equations. Let us imagine, or let us consider there is no relative motion along x and y direction. There is only the motion between the two frames in the z direction. So the Lorentz transformation equation can be written as x prime is equal to x, y prime is equal to y, since there is no change along x and y direction, and z prime is equal to z minus vt divided by root of 1 minus beta square, where beta is equal to v by c, and t prime is equal to t minus vz by c square divided by root of 1 minus beta square. So for finding the four-dimensional element, we make use of the Lorentz-Fitzgerald length contraction equation. So z1 prime minus z2 prime is equal to z1 minus z2 into root of 1 minus beta square. So dz prime can be written as dz into root of 1 minus beta square. Since there is no change along x and y direction, so dx prime is equal to dx and dy prime is equal to dy. Again, using the time dilation relation, t2 prime minus t1 prime is equal to t2 minus t1 divided by root of 1 minus beta square. So in simple we can write dt prime is equal to dt divided by root of 1 minus beta square. So now let us write the total or the volume element in S prime frame of reference, which is equal to dx prime, dy prime, dz prime and dt prime. So in place of dx prime we can write dx, dy and dz prime can be written as dz into root of 1 minus beta square, and dt prime can be written as dt divided by root of 1 minus beta square. So cancelling out this root of 1 minus beta square, we end up getting dx dy dz into dt, which is simply nothing but it is the volume element in S frame of reference. Hence we can say the four-dimensional or the volume element in four dimension in S and S prime remains the same. So under Lorentz transformation equation, this four-dimensional volume element remains invariant. Next problem goes like this. Show that the Lorentz transformation may be regarded as a rotation of axis through an imaginary angle I beta. So now let us prove that. So let us choose the four-dimensional space here with the dimensions x1, x2, x3 and x4. And we all know the fourth coordinate is the time coordinate and an imaginary coordinate which is given by ICT. Here x1 and x4 are rotated through certain angle. So that their new angles is x1 prime and x4 prime. Whereas this x2 and x3 remains unchanged. So we can write x2 prime is equal to x1 and x3 prime is equal to x3. Now we can write the new axis x1 prime as x1 cos theta plus x4 sin theta, and x4 prime is equal to minus x1 sin theta plus x4 cos theta. Since the fourth coordinate is imaginary one, let us also assume theta to be an imaginary one. So tan theta is equal to sin beta. These are our assumptions. Tan theta is equal to I beta, so that we can write sin theta is equal to I beta root of 1 minus beta square on cos theta is equal to 1 divided by root of I 1 by root of 1 minus beta square. So substituting the value of sine theta and cos theta in equation 1 and 2. So the equation 1 becomes x1 prime is equal to x1 divided by root of 1 minus beta square plus x4 into I beta divided by root of 1 minus beta square. So we have the value for x4, it is ICT, x1 plus ICT into I beta divided by root of 1 minus beta square. So upon simplifying, I into I minus I square, it's plus I square, it's minus 1, and C and C get cancelled. We end up getting x1 prime is equal to x1 minus Vt divided by root of 1 minus beta square. This is nothing but it is the first equation of Lorentz transformation equation. And let's see how the equation number 2 gets modified. x4 prime is equal to, so what is the x4 prime? It is minus x1 sin theta plus x4 cos theta. So it is minus x1, place of cos theta we are writing minus I beta divided by root of 1 minus beta square. It is sin theta, in place of sin theta we are writing minus I beta divided by root of 1 minus beta square plus ICT divided by root of 1 minus beta square. And in place of x4 we are writing it as an ICT prime. So on simplifying we get minus x1 I beta plus ICT. So it is t prime is equal to t minus v by c square into x1 divided by root of 1 minus beta square. So we could see this equation 3 and 4 represents the Lorentz transformation equations. Hence, we can say the Lorentz transformation equations are merely the rotation of axis in 4-dimensional space through an imaginary angle tan inverse of I beta. So we can say Lorentz transformations are nothing but it is a rotation of the 4-dimensional axis through a certain imaginary angle tan inverse of I beta. Now let us do the third one. Here goes the third one. Show that under the Lorentz transformation, the wave equation for the propagation of the electromagnetic potential del square phi minus 1 by c square into dou square phi by dou t square is equal to 0 remains invariant in form. So this question is also asked in other form, del square, the capital del square phi is equal to 0. So that means the D'Alembertian operator remains invariant under Lorentz transformation. We all know the Lorentz transformation equation and inverse Lorentz transformation equation. So x prime is equal to x, y prime equal to y, z prime is equal to z minus vt divided by root of 1 minus beta square. This 1 divided by root of 1 minus beta square is written as gamma into z minus vt. The same way t prime is written as gamma into t minus v by c square into z. Next we are going to write the inverse Lorentz transformation equation, which can be written as x equal to x prime, y is equal to y prime, z is equal to gamma into z prime plus vt prime, t is equal to gamma into t prime plus v by c square into z prime. Now let us compute what is dou by dou x prime, dou by dou y prime, dou by dou z prime and dou by dou t prime. We can write dou by dou x prime is equal to dou by dou x into dou x by dou x prime. So we are using the chain of chain rule. And dou by dou y prime is equal to dou by dou y into dou y by dou y prime. Dou by dou z prime is equal to, since z axis depends upon the two coordinates z and t, you are writing it as dou by dou z into dou z by dou z prime plus dou by dou t into dou t by dou z prime. And dou by dou t prime can be written as dou by dou z into dou z by dou t prime plus dou by dou t into dou t by dou t prime. So using the inverse Lorentz transformation equation, we can find out dou by dou x prime is equal to 1. In the same way, dou y by dou y prime is equal to 1. and dou z by dou z prime is equal to gamma, dou z by dou t prime is equal to gamma into v, dou t by dou t prime is equal to gamma, dou t by dou z prime is equal to gamma into v by c square. So now combine everything, that means we are going to put the values of dou x by dou x prime, dou z by dou z prime. In the above equation we get dou by dou x prime is equal to dou by dou x, dou by dou y prime is equal to dou by dou y, dou by dou z prime is equal to gamma into dou by dou z plus v by c square into dou by dou t, dou by dou t prime is equal to gamma into v dou by dou z plus dou by dou t. So we have the values of everything, dou by dou x, dou by dou y, dou by dou z, dou by dou x prime, dou by dou y prime, dou by dou z prime and dou by dou t primes. Now substitute everything in the D'Alembert value or D'Alembert operator, which is given by del prime square minus 1 by c square into dou square by dou t prime square. So this del square can be written as, the three-dimensional operator can be written as dou square by dou x prime square plus dou square by dou y prime square plus dou square by dou z prime square minus 1 by c square into dou square by dou t prime square. So substituting everything in the expression, we get, in place of dou by dou x prime square, we substitute dou square by dou x square plus dou square by dou y square plus gamma square into dou square by dou z square plus v square by c power 4 into dou square by dou t square plus 2 into dou by dou z vc square. That means we are expanding this dou by dou z prime. So you get gamma square into dou square by dou z square plus v square by c power 4 into dou square by dou t square plus 2 into dou by dou z into v by c square into dou by dou t square. So in the same way we can expand dou square by dou t prime square also. So in this we could see gamma square is common for both the expression, and it 1 minus v square dou square by dou z square is common there, and minus 1 by c square into dou by dou t square is also common. So and simplifying everything, we get dou square by dou x square plus dou square by dou y square plus dou square by dou z square minus 1 by c square dou square by dou t square, where gamma square can be replaced by 1 by root of 1 minus beta square, which is nothing but it is v square by c square. So in simply we can write del square minus 1 by c square into dou square by dou t square. This is nothing but this is the wave equation in S frame of reference. Hence, under Lorentz transformation equation, the wave equation of propagation remains invariant. So the equation of propagation of electromagnetic potential phi del prime square phi minus 1 by c square dou square phi dou prime square phi by dou t prime square is equal to del square phi minus 1 by c square into dou square phi by dou t square is equal to 0, which shows that the term remains invariant under Lorentz transformation. Thus, the D'Alembert operator del square minus 1 by c square into dou square by dou t square, which is given by del square, is also invariant under Lorentz transformation.